My name is David Thompson, and this is the second lecture in a series on dimensionality reduction. In the first lecture, I described some local methods for pattern recognition, which include nearest neighbor approaches and locally linear regression, among other things. This is the lecture where we really start to get into dimensionality reduction proper. I'm going to talk about what happens as we start going into higher dimensional spaces from those simple examples that I showed you before. In particular, I'll introduce a concept known as the curse of dimensionality, which is a perennial challenge for all sorts of pattern recognition problems. So it's something that you all should be aware of and know how to solve. All right, so the objectives of this lecture are to know how to find nearest neighbors efficiently. This is something that I really glossed over in the last slides, but as we start moving away from toy examples, this question will become more and more important, the notion of how to perform these calculations in an efficient manner. Because in a lot of cases, the naive approach really doesn't work very well. The second objective is to understand the curse of dimensionality. What is it? It sounds pretty ominous, and in fact it is. Like I said, it's a real challenge for scaling up these approaches to higher dimensional spaces. So you should know its implications for pattern recognition. And I'll also I'll whet your appetite with some idea of the general approaches that we'll use in later lectures to solve the curse of dimensionality. Okay, as a review, local pattern recognition involves inferring something about the process that generated the data or some underlying function of the data by looking in the local vicinity of your query point. Examples are k-nearest neighbor classification, local linear regression, and kernel density estimation. These all rely on the ability to find these nearest neighbors fairly quickly, or maybe beyond nearest neighbors, the notion of a range query, that is, finding points within a certain radius of your query point, which is a related problem. But in general, we're going to have to find a lot of nearest neighbors in data sets that could be as large as hundreds of thousands or even millions of data points. All right, so this is the case where we're looking for nearest neighbors with a one-dimensional data set. Here I've shown you the entire data set, X, right, which contains just a single attribute, right, so a single numerical input attribute, and we have a new data point which is here 4, and we're trying to find its nearest neighbor in this data set. So the question is, how do I do that efficiently? And the standard sort of naive approach to doing this would simply be to take the 4 and march down this list of data points and compare it to each one in turn, and keeping track of the closest neighbor that I found so far. So when I reach the end of the list, then I'll absolutely know with certainty which is the closest neighbor in the data set. Unfortunately, this sequential search actually takes linear time to accomplish, which means it's not that tractable computationally for very large data sets. The time required, the number of comparisons, grows proportionally with the number of data points. So if you get up to data sets containing, say, 1 million data points, this will be pretty onerous to perform. And it'll be particularly challenging if we have to do this as an inside loop in some other larger pattern recognition process, like, say, cross-validation, where we're changing kernel widths. We may have to try this once for every data point, in which case the total complexity of the algorithm would scale polynomially with the number of data points. So that would be 1 million times 1 million. That's a lot of calculations that you might have to do. So this quickly becomes intractable, and we need to find some more efficient way in order to generalize nearest neighbor to higher dimensions. Or to larger numbers of data points. So in the 1D case, there's a straightforward approach, which is to sort the list, right? So you can presume that we have some sort of strategy, some sorting algorithm that will, in sublinear time, let us sort the list into an ordered set of data points, and indeed these algorithms exist. So after we've sorted the list into our new representation in the computer memory, X prime, then we can actually search this space more efficiently. In fact, the standard way of doing this is called a binary search. So we take our query point and look at the midpoint in the sorted list and ask, is it greater than or smaller than this? And how close are we to that nearest neighbor? Or to that point in the data set. And based on the answer to our query, we can go left or right, up and descend down this what amounts to a branching tree of decisions, bifurcating the list at each time until we arrive at a neighborhood of points that are more or less, in this case, they're more or less equidistant from our query. Note that in just 3 comparisons here, we've already established the nearest neighbors of this point that is equidistant from between points 3 and 5, whereas before we would have potentially had to make 10 or 20 different comparisons to arrive at that same decision. The real advantage is the scaling property. Because we can eliminate half of the data set with every query that we perform, it scales with logarithmic time, which makes it tractable for large data sets. So it's a more efficient way of doing the same operation. So this is the 1D case. So how would we perform nearest neighbors efficiently in higher dimensional spaces? Well, it's not immediately obvious what the higher dimensional analog to the sorted list would be, but fortunately, researchers in the computer vision literature have dealt with this problem for a long time. They've come up with a wide range of data structures that will help us do efficient nearest neighbor queries in higher dimensional cases. And I'll show you one of the most common ones on the next slide. All right, so this is the KD tree, which works pretty well from anywhere from 2 to 8 dimensions of the input space. And the idea is to take your data set and arrange it such that it lies in a tree structure here at left, where each node splits the space with a hyperplane, right? And the points on one side of the hyperplane constitute half the data set, and the remaining half of the data set goes on the other side of the hyperplane, which lets us eliminate at each step, at each query point, about half of the data set. Now, which hyperplane do you use? Well, the most common choice to this is to cycle through the attributes one at a time. So you'd start and just split the data set along the first attribute, just like a regular sorted list. And then in the second level of the tree, the second tier of the hierarchy, you'd split on the next attribute and simply continue cycling through until you reach the end of the attributes and then start cycling again. And this it can be depicted graphically here at right. We have a data set of 6 points, and I've plotted them here in 2-dimensional space together with the different splits. So our first split is along that point A that bifurcates the data neatly into 2 halves along the x-axis. And then the next stage of the tree is the B points, right, which bifurcate the data, their respective data sets along the y-axis. And it continues on. And using this strategy, we can perform queries efficiently by eliminating half the data sets at each stage of the tree. So it's exactly the same computation benefits that we get from the sorted list, but here in 2 dimensions. So our typical search is order n log n. The computational properties tend to degrade at around 6 to 8 dimensions when it starts to look less efficient for nearest neighbor queries, and for that we'll need more sophisticated algorithms. But typically the KD trees are the first tool in the toolbox that I'd reach for nearest neighbor queries in the range of 2 to 8 dimensions. They can also be used for things like range queries. If you want to find all of the points in a data set that are within a certain range of a target point, then they can do that as well. And there exist lots of good, efficient implementations available that I hardly encourage you to avail yourself of. All right, so for higher dimensions, one typically uses an approximate nearest neighbor strategy. So this works for as many as a dozen or more dimensions. The basic idea is to leverage the fact that, well, for many of these data sets, we're most interested in an approximate nearest neighbor is almost as good as the actual nearest neighbor. So if we're willing to sacrifice those hard guarantees that we'll find the exact response to our query, but are okay with a little bit of error within some epsilon value that we define, then an approximate nearest neighbor calculation can give similar results. And so this tends to work better above 8 to 10 dimensions. And again, many refined implementations exist in lots of different programming languages. All right, so now I want to go on to talk about when some of these methods even fail beyond 15 or 20 dimensions. There are lots of cases where nearest neighbor methods just don't work for other reasons, and that involves something known as the curse of dimensionality. A more fundamental problem is when is nearest neighbor meaningful at all, right? And you can quite easily construct cases or data sets that are sort of pathological, where nearest neighbor queries really don't make much sense. And this is one. So we have a query point X in the center of our data cloud. Note that our training data, which are here represented as O's, are all more or less equidistant from our query point X. Right? So the fact that we go with one nearest neighbor or another is really sort of arbitrary. The structure, whatever structure is present in the data, really won't be captured by a nearest neighbor query. It will be very sensitive to the precise location of X in the input space. And you can say, well, this is a strange, crazy example, right? This would never happen in practice. But in the next couple of slides, I'm going to show you that for very high dimensional spaces, that is above a couple of dozen dimensions, every pattern recognition problem starts to look exactly like this example. right? Which means that the entire toolbox of local pattern recognition methods that we've established won't work for these higher dimensional spaces. One way to show this is to look at the volume of an n-ball. So an n-ball is just the higher dimensional generalization of a circle or a sphere, and it describes all of the points that are a certain distance from our target. Right? So this would be, so if we were performing a nearest neighbor-based classification or some sort of local pattern recognition strategy, we'd want a couple of data points in the local n-ball, right, in order to decide what the appropriate inference is at the query point. So this is the expression for the volume of an n-ball with a number of dimensions n. And note in particular the gamma function in the denominator. This is the real value generalization of the factorial function, right? And we all know the factorial function starts to go up very high, or very quickly for higher values, right? Beyond about 5 or 6, it really starts to explode. So what we're getting here is an exploding denominator, right? So that the volume of the n-ball relative to the volume of the hypercube that encloses it is actually decreasing, right? So here's the plot actually of the ratio. So I plotted here the ratio of the volume of the n-ball that's inscribed within a hypercube as the number of dimensions of our input space increases. You can see, just look at the y-axis here. We're already, for say 8 or 9 dimensions, we're already up in the hundreds, right? So what does this mean? This means that our inscribed n-ball, which I've shown here in 2 dimensions at right, comprises a much smaller portion of the input space, right? Most of the volume of these higher dimensional spaces is very far from the center of the n-ball, right? So if we were to evenly distribute a bunch of points in this higher dimensional space, it'd be very rare that any of them actually fall in the n-ball. They'd almost all be more or less equidistant from the n-ball outside it in these corners, which start to look extremely long and spiky in the higher dimensional spaces. This is kind of non-intuitive, right? Because we're used to thinking about these well-behaved 2- and 3-dimensional volumes. It's what we can visualize. But in fact, the properties of these high-dimensional spaces, the geometric properties, are not at all amenable to these sort of nearest neighbor approaches for just this reason. We've got all of our volume in these long, spiky structures that are far from the query, right? So everything starts to look like that pathological case that I showed you before, where all of the data is more or less equidistant, and it's very susceptible to noise in the input space and in the training data, right? So evenly distributed data points in high dimensional spaces are generally a bad thing for pattern recognition. So in summary, as dimensions increase, these Euclidean distances, that is these n-balls, become less and less meaningful. You can't interpret Euclidean distances easily. Uniform distributions become harder to sample, and in a fashion that grows, really explodes as the number of dimensions increases. Many parameters become polynomially harder to estimate as the number of dimensions increases, but most importantly, perhaps, and something that's often overlooked in the pattern recognition literature, it's just a lot more difficult to interpret your data and understand it and visualize it in higher dimensional spaces. We're restricted to seeing just these tiny subspace slices in 2 or 3 dimensions of data sets that actually have much grander structure potentially. So these are all challenges as the number of dimensions of the data increases. So are there any real-life problems where you have high-dimensional input spaces like this? Well, actually, they're the rule rather than the exception. So here's one great example. So face recognition, or any sort of object recognition, can be formulated as pattern recognition, where you're trying to classify images or image frames that could have many hundreds of pixels, right? So here we're looking at templates to try and decide which one contains a face and which one doesn't. The most obvious way to formulate this would be as a 20 pixel by 20 pixel input space, right? That's 400 dimensions in your input space. So we're well into the range of super high dimensional spaces for which local pattern recognition strategies won't work as well, right? And face recognition, it's obvious that it works, right? We've got cameras that can do this, but in order to actually get pattern recognition to operate, we're going to need some sophisticated pre-processing strategies to reduce the dimensionality. Another domain where these sorts of higher dimensional input points are common is in the science that's more in the Earth and space sciences realm is in spectroscopy. Often in spectra we're describing individual data points by many wavelengths. So here we have reflectance spectra, which are measurements at many wavelengths of light here, from 350 to about 950 nanometers. These reflectance spectra can easily be tens or even hundreds of dimensions in size, right? And yet we need to find a way to perform pattern recognition on these data sets too in order to distinguish spectra or classify them, and we're going to need more sophisticated methods to do that. All right, so I want to close with a couple of, by whetting your appetite with a couple of solutions. So one solution to the curse of dimensionality would be to rely only on those pattern recognition methods that are intrinsically robust to higher dimensional spaces, right? So we've talked in previous lectures about random forests, for example, which tend to do pretty well in higher dimensional spaces. So you could limit yourself to those pattern recognition strategies. Now that's kind of limiting, and there are other ways we can tackle the problem. And in particular, we can try to represent the data differently. So we can use handcrafted features. We can use a subset of the features. In the next lecture, I'm going to talk about feature subselection strategies that will let us reduce the dimensionality by choosing, just selecting particular features that are more informative than the rest and performing our pattern recognition on those. We can also come up with linear projections of the input data set that will reduce the dimensionality so that it's more amenable to our local pattern recognition approaches. And then in the final lectures, I'll describe some nonlinear projection strategies that will allow us to reduce dimensionality in nonlinear ways. All right, so in summary, I described some ways to find nearest neighbors in data sets, sorted list for 1D, KD tree for 2 to 8 dimensions, and above that you'll want to use approximate nearest neighbors. But far above that, most of these local pattern recognition methods will fail because of the curse of dimensionality, and so the coming lectures will provide some solutions to that.